All right. Um, Good afternoon, class. Um, I'm trying a different method of delivering the lessons today. What I'm doing is I'm streaming directly within the YouTube, um, within my YouTube channel instead of using some software to go into YouTube. So I'm hoping it won't lag as much. I don't know. Give me some feedback in the live chat if you have it. So what we're going to do today is we are going to finish up RC circuits, okay? So you might recall that we were studying circuits that looked like this, RC circuits. And when you have an RC circuit, we solved that the charge on the capacitor as a function of time is given by Q naught times e to the minus t over tau, where tau was equal to RC, time constant. So what we want to do when we're solving RC circuit problems is we need to figure out what is, oh, hey, Selma. Hey, Luigi. How was the barbecue steak? The barbecue steak was excellent. Hey, Aisha. Hey, Luigi. Hey, Rourke. Hey, Potato Master. Who's Elite Pro? I don't even know who is Elite Pro. I don't even know who Elite Pro is. I'm gonna guess it's Will. Hey, Mina. Hey, Alexis. Hey, Steven. So we wanted, basically what we have to do, oh, it's Mohammed, okay, is we want to determine Q naught and we got to determine tau. And once we determine both of those things, we can just plug it into this formula and then we're good to go. All right. Do a couple of examples here. So for example, what if you had an RC circuit that looked like this? What is our time constant going to be in that case? Well, in this case, you can see that the capacitor is discharging through the parallel combination of R1 and R2. So when we talk about the R in this time constant equation, that's the resistance as seen by the capacitor. So we can see that the capacitor is seeing both of these resistors in parallel. So our tau is going to be R1 in parallel with R2, whatever that is, times C. Okay. Similarly, I don't know, like that. And that's R1 and that's R2. In this case, you can see that the capacitor is discharging through the series combination of R1 and R2. And so in that case, our tau is going to be R1 plus R2 times C. All right. So depending on, I think that takes care of how to determine time constant. Now we have to determine how do we get Q naught. And to get Q naught, we want to use the fact that for DC circuits, which is what we're dealing with for now. So for DC circuits, after the current through the capacitor is going to be equal to 0. Oh, the current through the capacitor is going to be equal to 0. Now, why is that? Why does the current through the capacitor become 0 after a long time? Well, capacitors are either charging or they're discharging. So if you wait long enough, it's either going to be fully charged, in which case the charge becomes constant, or it's going to be fully discharged, in which case the charge becomes zero. Okay, so basically after a long time, the charge is just going to settle into whatever it's going to be. That's with DC. If you have an alternating current where the current is changing, then that means that basically the current will keep going through the capacitor. But in DC circuits, inevitably the current is going to become zero. So let me show you how that would work. What if I had a battery and I had a capacitor is connected like this. Okay. So maybe this is a 1 nanofarad capacitor, and this is a 12-volt battery. And maybe this is a 2 ohm resistor, and this is a 1 ohm resistor. Okay. And I want to know, what is the charge on the capacitor after a long time? So in order to figure that out, what we would do is we would use the fact that after a long time, the current through the capacitor is zero. So we could basically just ignore the capacitor, okay? And if we ignore the capacitor, we can see that this is just a voltage divider circuit, okay? And if you have a voltage divider circuit with a 2 ohm resistor and a 1 ohm resistor, that's a total resistance of 3. So you can see that the current, now that doesn't mean that the current through everything is zero, because the current through the capacitor is going to be zero, but the current will keep flowing through this part of the circuit after a long time. So the current that flows is going to be V over R, which is 4 amps. Okay. And then, so that means 4 amps is flowing through this 1 ohm resistor. So the voltage across the 1 ohm resistor is going to be equal to I times R. So it's going to be 4 times 1 ohm resistor. So according to Sipov, series things have the same voltage. So the voltage across the capacitor is equal to 4 volts as well. Then to get the charge on the capacitor, I would use CV, which is going to be 1 nanofarad times 4 volts. And so see how I have 1 times 4, but then I also have a nano. So that's going to be 4 nanocoulombs. A more difficult example here. Here's an example. And we want to, so basically, so the switch is in the left position for a long time. Okay. At t equals 0, it is switched, it is moved to the right position. Okay. So basically what's going to happen here is when the switch is going to in the left position for a long time, that's going to determine the initial charge on the capacitor. Once the switch moves to the right position, the capacitor is going to discharge, and then we'll be able to calculate what the time constant is. Okay, so so what you want to do is you want to analyze the circuit basically before t equals 0 and after t equals 0. So before t equals 0, okay, before t equals 0, the switch is in this position, and so we can basically ignore those two resistors because these two resistors are connected to a dead end. So we just ignore that part of the circuit. So the circuit before t equals 0 looks like this, essentially. 12 volts. And 8 nanofarads. Okay, so do you see? So after a long time, remember it's been in the left position for a long time. If you have two 6 kilo ohm resistors, two equal resistors in a voltage divider, each one is going to get half the voltage. Okay, so this 6 kilo ohm resistor is going to get 12 volts, or is going to get half of the voltage, which would be 6 volts. Okay. Now the capacitor is in parallel with that resistor. So that means that the 8 nanofarad capacitor gets 6 volts. So that means, according to Q equals CV, that means that the C value is 8 nanofarads and the voltage is 6. So we would get that Q naught equals 48 nanocoulombs. Don't forget that nano. All right. So that's my Q naught. So once I know the Q naught, I can use that in my equation here. Okay. Now, I see the video is fuzzy. Can you still read what I'm writing, even if it's fuzzy? I hope. If it's too fuzzy to read, then I will rebroadcast another way. Probably not today, but another day. Or I'll just take a picture of the notes and you can listen to the lesson. Let me know in the live chat if you want me to take a picture of these notes, and then I can just post them on the Discord. All right. So now we're going to analyze it after time 0. So after time 0, the switch is moved into this position. So now, once we've moved the switch into that position, this part of the circuit is blocked out. And you can see that the capacitor is discharging through actually 3 resistors in parallel. Okay, so we actually have, after time equals 0, the circuit looks like this. So we have 12K, 12K. Um, 6K and 8 nanos. Okay. So if we look at this capacitor, you can see that it's actually discharging through 3 resistors that are in parallel with each other. Okay. So that means that our time constant is going to be 12K in parallel with 12K in parallel with 6K. times the capacitance, which is 8 nanos. All right. So I'm not going to work out the math, but if you do 12K in parallel with 12K in parallel with 6K, it's going to give you 3 kilo ohms. And then 8 times 8 nanofarads. So that gives us now a kilo. I'll write this down here. A kilo is the third. A nano is 10 to the minus 9. So what happens if we do a kilo times a nano? Kilo times a nano is going to be 10 to the minus 6, which is called a micro. Okay, so I have 3 times 8, that's 24. And then I have a kilo times a nano, which is a micro. And then an ohm times a farad is just a second. So my time constant is 24 microseconds. So that's the time scale on which the capacitor will discharge. It's going to be literally microseconds. So now I'm going to take these two things and I'm going to plug them in to my Q of T equation. So my Q of T equation is going to be 48 nanocoulombs times E to the minus T over 24 microseconds. That's the answer. I don't know, let's say 8 microseconds. Well, what I would do is I would plug in 8 microseconds here. 8 microseconds divided by 24 microseconds, that's 1/3 of a microsecond. So I would have 48 nanocoulombs times E to the minus 1/3. Let me put that into my calculator. Uh, 48 E to the minus 1/3 gives nanocoulombs. All right. So this is the IB exam, or not the IB exam, the AP exam especially likes to give these questions where you have a switch that's in one position for a long time and then it's moved at time 0 and you have to get, I don't know, Q of T or something like that. All right. So that's my lesson for today. Sorry to disappoint you that you're not seeing my face. Please give me feedback on whether I should go back to the old way of doing things or if this is better. Please do the homework before Sunday and on Monday. Bye now.